tree coming. Coming. Gloriousness, happiness.
I sent you an email saying I enjoyed it so far.
Yes, that was good. So we have at least a few votes of confidence for Git for working on projects with other people.
Oh, yeah.
It actually does work, right? It can make it easy for two people who aren't sitting at the same terminal, write code, throw it into Git, pull it down, make some changes, throw it up, and be able to share it back and forth. That's what it's for. And a lot of people use it, and there's reasons why. All right. I thought I did this in here, but according to my notes, I didn't. So if I've done this in here, stop me. But what I'm going to do is look at this recursion business for traversing a tree and give you one different view of what's going on. So there's a typical tree that may have been built, and it's in order, and we had this in order traversal method, which looked like this. So it said if tree left is not null, traverse tree left, and then print tree data, and then if tree right is not null, traverse tree right. And the challenge of sorts here is to make peace with this idea, one, that this is calling itself, and that that's okay, and two, that we're never actually doing anything except printing the root of a tree, but somehow this prints the entire tree, and it prints it in order. And trying to trace through this code and figure out how we get the whole tree printed out from this can be a little daunting at first. So I want to take one more spin through this and kind of get an idea of what's going on. So the first thing we're going to do is we're going to try to traverse that tree. So we're going to just call traverse. We'll say traverse. And we're going to pass it this tree. Where we're actually passing it a pointer to the root. But that's the effect of what we're passing it. We're asking it to traverse this tree. And it has to do three things. So let me call these step A. Well, I'll just call them A, B, and C.
Is that tree wrong though? Shouldn't it be 28, then 10 and 5?
Yeah, I did something wrong. That's an 18. Thanks. That would have been tricky later. All right, so we call traverse and we pass it this tree. And our algorithm will do exactly three things. First, it will look at tree.left, which is this tree, 10, 5, 18, and it will say, is that null? And if it's not, it will say traverse this tree, 10, 5, 18. Okay, at that point, we're calling a function. named traverse. So we'll come over here, and here's how we execute traverse 10, 5, 18. Well, the first thing we do, so this was step A. First thing we do is step A is the left subtree of this null? And it's not, because the left subtree is this tree containing a 5. So we're going to make a call to traverse, which says traverse, and it's just this single tree. All right, that's going to require us to make a subroutine call. So here's what happens when we say traverse 5. Step A, is the left subtree of this null?
Yes.
Yes, so there's nothing to do. Step B, print the data at the root. So this will print 5. And so here's our output. And it's printed a 5. Step C, is the right subtree null?
Yes.
Yes, so there's nothing to do. And at the end of this, I'll go ahead and be explicit, I'll say return. So step D, return. Where do we return to? Right after the place that we were called from. We were called from here, so we return up to here, where we now do step B, which says print the root data of this, which is a 10, so it says print 10. And now 10 appears on our output. And then check the right subtree and see if it's null. It's not. It's the node 18, so traverse that. And so we're going to make a call to traverse. And the traverse algorithm has 4 steps. Step A, is the left subtree null? Yes, so there's nothing to do. Step B, print the root node's data, so print 18. Step C, is the right subtree null? Yes, it is, nothing to do. Step D, return. And we return right after where we were called from. So we come back right here, and now we're ready for step D, which says return. And we return right after we were called, which is step B, which says print the root data, so we print 20. And then one more thing to do, traverse the right subtree, which is 40, 30, 56, and this will go off and do a bunch of things, which will eventually print 30, 40, 56, and will eventually return back. And then step D, return. And we exit from our call to traverse, and we're done. So that's half of what's going on. I skipped entirely the details of step C over here. But it just keeps calling itself with different arguments. The magic is twofold. One, the fact that this actually does what you want it to do. Two, that it actually comes out of it.
Basically, have to rewrite all of this.
Yeah, no, yeah. You have to show like that.
What did you get for the course on physics? Did you get a number? Oh.
There's a man who knows how to finish.
All right, let me go over the one-day program while we wait for more people to show up, and I'll hand back the midterm, and then we'll mostly talk about the midterm. So ODP 13 is posted. It's due tomorrow morning at 8. The goal is to initialize the tree node. So the basic node in our tree can look like this. Struct node, and it's got a left pointer, a right pointer, and a piece of data. Okay, so the data for our case is just going to be an integer, and left and right are pointers to struct nodes. And make sure you use the structure, don't change the order of those fields, because things won't link properly. If you do. So you want to write a function named init. It takes an integer and it returns a struct node pointer. Okay? And all init should do is basically create a new struct node, set the left and right pointers to be null, and set the data to be whatever value you pass in. Okay? Fairly straightforward once you get everything lined up the right way. An example of how you might use it might be declare a variable to be a struct node star, and then just set that variable equal to init and give it some integer. After you do that, my tree should be a struct node pointer, which means my tree arrow left should be null, my tree arrow data should be 15, and my tree arrow right should also be null. And you want to use malloc to create this new node. Okay, so make sure you're allocating the right number of bytes, size of struct node, not struct node star. And make sure that if you call this and you create 3 or 4 nodes like this, that you actually have 3 or 4 nodes. In other words, I should be able to make a node with a init 15 and an init 20 and an init 30. And when I go back and I look at each of those 3 nodes, first one should have a data of 15 and then 20 and then 30. Right? If all of them end up having the same data value of 30, you're not really doing dynamic memory. You're somehow using a static variable and just pointing to that. So do all of that, test it, make sure it works, and then link it into the test code and run assess. And a number of people have already done this, so it seems to work. So assess it with the test case and then run it with the G command to get a grade. So that's due tomorrow morning at 8, and then tomorrow another ODP will open, which will have you actually create a tree containing 3 nodes. So it'll be like a init, but I'll actually pass you 3 integers, one to the left, one to the root, one to the right. And we pieced some of that together on the board yesterday. So that'll go up tomorrow at 8. All right, let's go over the exam. So the first thing to note, if you haven't seen the announcement yet, is a lot of people had trouble with the stack question. So I'm offering you an opportunity to redo the stack question. Okay? And there's instructions in that announcement. Basically, I posted a 1-page PDF that has that question. Print that out, put your name on the top. Do it correctly, carefully, and attach it to your original midterm and turn it in to me by, I think I said Thursday. And I'll regrade it and use that. Okay, but you gotta follow the instructions exactly, right? If you turn that in without the midterm, I can't grade it. If you try to write in a different color on your original midterm instead of doing a new copy, I'm not gonna grade it. Okay, so make sure you know how to do it. The other thing is, you need to do this as if it's a take-home test. Okay, don't talk to anybody about this. If you're not sure how to do it, you can come and talk to me. Okay, but it's test conditions. Okay, imagine that you're sitting in the room. You can't lean over and say, hey, when you pop from an empty stack, what's the stack pointer become? Okay. If you have questions, I'm happy to talk to you. Send me an email or come by my office. But don't talk to anybody else. That's the one caveat. All right, Saeed. Spencer Bacon. All right, so let's go over this. So question 1, we were setting up a data structure with these 4 fields, parse are a single character, an integer, and an array of integers. So, and this is called data, so struct data. That says we're going to define this data structure. A string named name, so a string is a car star, so car star name. A single character is just a car, so car department code. And if you say department code bracket 1, that is not a single character, that suddenly becomes a string, and it's an address in memory, and everything will go crazy. So if you want a single character, it's just a car. Single integer named year is just integer year. Bless you. And then an array of integers named grades, so integer grades. And we want 10 integers, so bracket 10. We start counting indexes from 0. But if you say array bracket 10, it will hold 10 integers. Okay? But they're numbered integers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So they go up to 9, but it actually holds 10 integers. And if you want 10 integers, you gotta put a 10 there. Don't put a 9, don't put an 11. Okay? The only thing that's funny is when we count from 0. So the index of the last element is grade bracket 9. Okay? But this is not accessing element 10. This is just the syntax that we're using to say we want to hold 10 integers in here. Okay, so there's some confusion about that. This does not work. The compiler will complain, right? And I suggest just avoid the bracket notation. It's an added convenience, it's more human readable or something, but it's not what we mean. We mean a car pointer, right? And the more you stick with the language of pointers, the more natural they're going to become. I would say the only time you really want to use brackets is when you're specifying a size of an array, right? And by itself, you can do this to represent a car pointer, but it's not the same thing as a car pointer. And inside a structure, it'll complain unless you put this at the very end of the structure, because it doesn't know how to pack things in into the array otherwise. All right, so that was it for part A. Part B, declare a variable named student to have type struct data. So struct data star. That's pretty much your only option. You can type def and then use type def or something. Right? And you gotta have that pointer. Otherwise, if you just say struct student's not a pointer, it's actually a struct data. All right, and then a malloc statement to set student to point to a block of memory large enough to contain struct data. So that just screams out something like this: student equals malloc size of struct data. Do I want struct data or struct data star in here? Struct data, because I'm trying to allocate enough space for a struct data. This is going to point to that block, but the block itself is supposed to be a data. So it's got all of this stuff in there. All right. Part D, we want to load values into the fields of this structure. So we want to initialize student with the following values. So the name is the trickiest one, probably. We have a car star, but it's not starring to any particular place in the memory. We've said it's a pointer, but we haven't told it what to point to yet. And if we try to string copy into student arrow name, we're probably going to segfault. So you've got two options here. One option is the following. So student and student's a pointer, so to get to a field, we have to use the arrow. So student arrow name equals Malik 5, or 1 plus string length of Nick, or 1 plus string length of Nick times size of car, or whatever, but essentially 5 bytes. And then string copy, student arrow name, and copy your string into it. So that will definitely work. So will this, but it does something very different. That will set things up so that if you look at student arrow name, you see the string Nick. But it's doing something different. It's telling the compiler to create a string in memory that looks like this, and it's saying set this to have the address where that string has been stored. And the danger with that is if you try to do something like student arrow name bracket 0 equals S to change this into sick, that may or may not work at runtime, depending on whether the string is stored in a writable area of memory or a protected area of memory. So if you really want to have a block of memory that you have access to, right? Create a block with malloc, set student to point to it. Create a block with malloc, have the name point to that block, and then you can string copy into there. Okay, but I gave full credit for either of those. They both do work. Department code. So department underscore code. So we can set that equal to the character C. Again, if you double quote C, that's not a character, that's a string. And so it's going to take the first byte of an address, and that'll be wacky. Student arrow year equals 2012. And then the grades. So there's a number of ways to do this. Some people just did 10 assignment statements, that works. But I didn't leave you enough space to do that easily. That was a bit of a hint. It's easier to do this with some sort of loop. So we could do something like for integer I equals 0, I less than 10, I plus plus. And we could say student arrow grades bracket I equals, and then here you got to figure out the equation. So I is going to start off at 0, and we want it to be equal to 10. So something like 10 minus I. And it finishes when I equals 9, 10 minus I is 1. So that will assign the grades. So a lot of people use dots instead of arrows, so that was just 1 point total. A lot of people, well, several people, wrote something like this. And technically that works, and I'm okay with that, but I want to be sure. If I saw it from one person, I think they were just trying to be really clever. But when I see it from several people, either several people are trying to be very clever or are not quite sure on the difference between an array and a straight pointer. I mean, this is perfectly correct, right? But to me, it makes me wonder if there's some confusion about declaring something as a pointer. You can do it like this as an array, but if you don't intend it to be an array, you don't have to do this. right? You can just say pointer, arrow in the field, that'll dereference the pointer and pick up that field. So I want to make sure, if you did this, that you understand why you did that and why it works and that there are other options. And as long as you understand that, right, I have no problem with seeing that. But it's likely to be confusing down the road, especially when you go back to the code and you think this is an array, but you only access element 0. What else? So some people did this, and that is kind of a compile time thing. If you're initializing an array, if you say integer x bracket 10 equals curly bracket and you list the values, that'll work, right? The compiler will set that up. When it creates the array, it'll load those values into memory. But inside code, if you just say student arrow grades equals, that's not part of C. And the compiler will complain about that. Yeah.
So would you recommend doing something like that over there, or something like this one?
So that was a singular case. So can I put that on the board?
Yeah, go ahead.
So let's see. So this will work. Okay, you can initialize structures by just listing the different fields with commas in between. And even the grades piece you can pick up with another list in brackets. The problem with this is not the same student that we defined in part C. In part C, we created student to be a pointer to a struct node, and we set it to point to some block of memory. And then in part D, I wanted you to initialize the values of that variable. This actually creates a new variable, which is no longer a pointer, it's actually a struct data, and has nothing to do with what we did in parts B and C. But it will initialize it, so if you're just trying to initialize a structure, right, that's valid syntax. Yeah.
Would it work if you dereference? Is there a way to like dereference the students instead of struct data, so you could be like star?
I don't think so.
That would work.
Maybe there's a trick, but I don't know it. I think if you said struct data star student equals, then you can initialize it to a pointer, which is what we do when we write integer I equals 0 something. All right, I think those are the main things on that one. So let's talk about the linked list. And let me make a general comment here also. I was actually really happy with what I saw on the exams by and large. Even though there were some lower grades, the programming questions people mostly tended to get right, or more right than wrong. And the grade drop was really the hash question and the stack question. And some people dropped 40 points on those two questions. So that's a big contributing factor for the lower numbers. The stack question you get to redo, right? The hash question, I don't know what happened on there, but we'll go through it, and hopefully you're clear on hashes by Friday, because you've got programs to turn in on Friday that do hashes. But by and large, the programming questions look good, including this one. So this is a linked list, and let me put it on the board so we can write on it. So this is a 0, 6, and a 4, and this point's here, this point's here, this point's here. So linked list, sentinel node. So 3 data nodes, a 6, a 4, and a 1. All right, and this is all built around a struct node. With an integer data and a struct node star next. All right, so question 1, what would be printed by the following statement? LL next data and LL next data. Okay, this is LL, it's the sentinel node. This field down here is LL arrow next. Right, that's how we access that field. We say take the thing that LL points to, pick off the next field. Which means if we look at the thing that LL next is pointing to, it's this block over here. Which means this field is LL next. Right, this is LL arrow data. This is LL next data. And this is, that's probably as far as we have to go. This is LL next data. All right, so we're printing out LL next data and LL next data. Next data is right here, that's a 4. Next data is 6, so it prints a 4 and a 6. And most people at least got a 6. Some people were off by 1, so they thought it was 0, 6. The 0 would just be LL arrow data. The data field of the thing LL points to. So make sure this clicks for you, right? Before too much longer, right? This is fundamental, okay? Write some C code to delete the last node of the list without using any loops or conditional statements. Only like 1 or 2 people used any temporary variables in here. And that was what I was picturing, was having a temporary variable that you would, point to the last node and so on. Most people just did LL next, which you can do. So we want to delete the last node. What does that mean? Did I tell you to free your memory? Yes. So we need to free this node, and we need to set this to null. Okay, so to free this, we need to find it. Well, this is LL next data. This field here is LL next. So we want to free LL next. And then we want to set this equal to null.
How would you use a temp variable?
So here's a different way to do this. So we could say something like, so here's my temporary variable. T equals LL arrow next. So LL arrow next, that's the 6 node. T equals LL arrow next. That's the 4 node. So now T is pointing to that 4. So free T arrow next. And then T arrow next equals null.
With that second line, would that be T arrow next?
Yes. Yeah. So move down the list. It's exactly the same thing, it's just more steps. But it lets you sort of draw pictures on the paper instead of trying to count and make sure you get the right number next. But we're still freeing LL next, next, next. And then we're setting LL next, next, next to be null. So it's the same thing. All right, and then part C, create a new node and point to it with a variable named new. So create a new node. I can get rid of this at this point. So we want new to be a pointer to this node, so I'm going to say struct node star new, and I'll malloc size of struct node. That'll work for part C. And I didn't need functions here, right? I just wanted some C code. If you did functions, that was okay. But I really just wanted C code that creates a new node and points to a variable named new. And then D, we wanted to insert it in between the 6 and the 4. So right here, so here's our new. And I didn't tell you what value to give the number, so you didn't have to give it a number. I just wanted to squeeze it in between here and here. So, so how do we do this? We basically need this to point over here, and then we need this to point to the new node. So if you have this labeled from before, we can do the following: new, next, which is this block down here, should equal wherever this thing is pointing, which is LL next, next. And then this block should now point to new, so LL next, next, should equal new. And the number of people inserted before the 6, some people inserted right here that just did LL next equals new node, and new node equals LL next. It's easy to reverse the order of these, and that does not do what you want. Because if the first thing I do is LL, let me do this in red. If the first thing I do is LL next, next equals new, that changes this to point to my new node. And then if I do this first statement, new arrow next equals LL next, next, that's saying take LL next, next, which is a pointer to this, and set new to point to that. And this is what your list looks like.
So we have to make sure we don't lose the node.
Don't lose the node. So you could put it in a temporary variable if you wanted. Some people did that. But before you throw it away, make sure you're done with it or you saved it somewhere. All right, third question, doubly linked list. Without too much that I really needed you to do. So, struct node. So we've got a data and a previous and a next. And here you are writing a function, you're writing an insert function. It takes a list, right, which is a sentinel node pointer, and it takes a number, and you want to create a node to hold that new number and put it at the beginning of the list, which means right after the sentinel. So here's list, and it's going to point to some sort of sentinel. We don't know what the previous might point to, but the next will point to our first node. This is some data. This points to our second node, and this points back to our first node, or maybe it points to null. It should probably point to null, but a lot of people just had it pointing to the sentinel. So to make a new node, we need to do something like this. So this is in void, insert struct node, LL, and integer num. All right, first things first, create a new node. All right, so I'm going to say struct node star new equals malloc, size of struct node. That makes our new node that we're going to squeeze into the list. Set the data equal to num. So that's set up. And we want to put it in right here. So we need to do the following. The sentinel has to point to this. This has to point to what used to be the first data node. What used to be the first data node needs to point backwards to this. And this needs to be either null or point backwards to the sentinel. All right, the order can make a difference. So the things that I need to do with this node, the things that I need to do that require information from this node, I'm going to do first. And you can use temporary pointers here if you want, but let's just bang it out. So list next. This is list next, so that's this node, and let's set its previous equal to our new node. So that will change this to point to here. And this I want to set to point to what used to be the first node. So I can say new next equals, where how do I find my first node? It's just list arrow next. So that sets this to point over to here. And now we're done playing with that node, so we can modulate the other fields as we like. So list next equals new. And that takes list and has it point to our new node. So going forward, list points to this points to data, and that continues. Going backwards, data points to this needs to point to either null or our sentinel node. So new arrow previous equals, I would say null, but I also was fine with list. Or you could set it to whatever this had been pointing to. If you didn't know which it should be, that would be safe also. So before we change that, we could have said new previous equals list next previous. Because when you're going backwards, you get to the end of the list, we usually set it to null to say there's nothing prior to that. If we just pointed to the sentinel node and we don't constantly compare that to our sentinel node, we don't know that we're in the sentinel. So going forward, the last node points to null. Going backwards, the first node points to null. But we didn't go over those details very carefully, so I think either. So something along those lines will get you there. And I graded this one fairly gently. So Most good attempts got at least half credit. But this was one of these questions where, you know, if you offered me $1 million, if I could rattle off those 4 instructions, I wouldn't be able to do it. Right? I just don't have them memorized, but I can recreate them by doing this kind of analysis, right? So that's in that spirit of being able to take a data structure and write code to correspond to certain things you want to do to it. And you'll definitely see questions like that again. All right, was there something else I needed to say on this one? I thought there was, but can't remember it. All right, let's talk about hashes. If you have questions while we're doing this, please ask them, because I need to run off after class. So hashes, how do we hash? We have a hash function. And it takes a number and an attempt. And our simplified function here was just n times the probe modulo 11. And the goal was to figure out where each of these numbers gets stored in our hash. I gave you a space that you could use to draw a hash table. I think almost nobody did, and that's okay though. But I'll draw one here. So the first command is store 5. So we're going to run this through our hash function. We're going to say hash 5, and we always start with the probe equal to 1. So I put a reminder up there. So what is hash of 5 comma 1? It's just 5 times 1 modulo 11, and 5 times 1 is just 5. Okay, and it says assume the hash table is initially empty, so this is all empty. So storing 5 says we should try to put this in location 5. Location 5 is available, so we put our 5 there, and that's the only thing we need for part A, just 5, and that's successful. Now we store 10, so we hash 10, comma 1, which is 10 times 1 mod 11, which is 10. We check index 10, that's available, that's where we store our 10. And again, we're successful on our first attempt. Store 22. So we hash 22 comma 1, which is 22 times 1 modulo 11, which is equal to 0. We check index 0, that's still available. So we store our 22 in here, and that's your only answer for C. Now we store a 21. So we hash 21 comma 1, that's 21 times 1 modulo 11, which is what?
It's 10.
That's 10. So this says we want to store the number 21 in index 10. That's a collision. So we have to hash again with a probe number of 2. So that calculates 22 times 2, which is 44, which is congruent to 0 modulo 11. And we try to store in cell 0, and that's a collision.
It's 21 times 3.
I knew that was wrong. Thank you. All right, so that's 42, which is 9 modulo 11, and cell 9 is available, so that's where we store our 21. So your answer for part D is 10 comma 9. And then we try to store 16. So hash of 16.1 is 16 mod 11, which is congruent to 5, and that's a collision. Hash 16 comma 2 is 32, and that's 22, that's congruent to 10, and that's also a collision. So we hash with a probe of 3, and that's 48 mod 11, which is 44 plus 4, that's congruent to 4, and cell 4 is available, so this is where we store the 16. So for part E, your answer should be 5, 10, 4. If that's not clear, right, we need to talk, because you need to be able to do this to implement PA3, which is coming up in a few days. So definitely ask about this. Big empty space. Short answer is if a hash table has a length of 101 and uses probing to handle collisions, what's the largest number of items you can store? 101. Right, so some people said 100, I think they were thinking of queues. For a hash, each cell can hold a number, so the table can be filled up, 101 entries. If an entry is deleted from a hash, can the spotted occupied be reused? Sure. If not, your hash wouldn't be very useful. But we have this deleted flag that tells us whether or not something has been deleted. And when you're looking for an item, if you reach a spot that's not in use, you don't know whether that item was in your table or not. Because if this item was deleted, it's possible that when you tried to store the item you're searching for, you got a collision here. So if it's not in use, you don't know if you're done unless the deleted flag is also clear. So it's not safe to stop as soon as you see that it's not in use. So H, the answer is no. But I, when looking for a place to save an item, if you reach a spot that's not in use, is it safe to use it? Yes. Doesn't matter if it's been deleted or not. If it's not currently in use, you can store something there. And then smallest and largest number of cells to check if you're looking in a hash with 17 cells, largest number of checks you might have to do is 17. It's possible that each time you hash, you'll hit another cell that's occupied, and you'll have to keep hashing until you check all the cells. Smallest number will be 1. You hash once, and there's your number. I remembered what I needed to say about this. That's not it. On this previous question with the doubly linked list, there's a detail in here that only one person picked up on, and I didn't mark off for it. But if your list is initially empty, if all you have is a sentinel node, you need to do a little bit of special handling. Because when you try to set the first data node previous to point to your new node, you need to make sure there is a node there that has a previous field. So if the sentinel points to null, you can't talk about list arrow next, arrow previous, because that'll say fault. So you need to do an extra additional check there. All right, I'm not talking about stack question because that's your do-over. 1 minute, let's see if we can do it. So repeat of an old quiz question, right? Which of these is not interacting with a queue as an abstract data type? That would be C, right? Head and tail and module 1000 are not part of the definition of a queue. That's using the way that the queue was implemented to do something, and we don't want to do that if we're seeing it as an abstract data type. So C is the outlier there. Which of the following could potentially cause a seg fault? So this is saying x is an integer, y is the address of x. That's always safe to say, and we're printing out the address. That's perfectly fine. This is just taking z, setting it equal to x plus y, and printing z. That's perfectly fine. This is saying y is a pointer to an integer, set y equal to the address of x. And when I say star y, the thing that y is pointing to is x, so star y is just x, so this is just printing the value of x, so that's fine. But this one, x is a pointer to an integer, y is equal to whatever x is pointing to. We don't know what x is pointing to. So when we try to do this assignment statement, we might hit a seg fault. And that's the classic seg fault from pointers. Allocate space for 125 elements of type struct big, so malloc size of struct big times 125. If you did it with a static array declaration, I'd let you get away with that. Utility to help detect memory leaks, that's valgrind. What would you type to compile a program named main.c? So anything along these lines, the easiest being gcc-g main.c, that gives you an a.out that you can compile, but you could also do -o main and other stuff. -g is not a command, because you said -g, you didn't get your point. If your directory contains a make file, what command do you type to build the program using the make file? Make. Write a statement that allocates 10 bytes of data, assigns a variable to it named pointer, and prints an error message. So pointer equals malloc 10, gets you 10 bytes. If pointer equals null, then you're out of memory. All right, we're a minute over. Come and talk to me if you got questions on this. If you have stack questions, otherwise if you want to redo the stack, go ahead and write that up and turn it in by Thursday.
Part of the second question, they all